So this is a video on substitution reactions. If you get asked to define what a substitution reaction is, there's really 2 points that you need to make. The first one is that substitution reaction is the replacement of a ligand in a metal complex by another external ligand. The second point is that there's no change in oxidation state or coordination number of the metal centre. So we define its ability to do this in terms of kinetics and not thermodynamic stability. So the kinetic terms you need to know are labile, which is rapid substitution, and the way I remember this is that the definition of labile is that it is liable to change, and if a complex undergoes slow substitution, it's inert, which by definition means lacking ability or strength to move. So for labile metals, the D configuration is 1, 2, 7, 9, 10, high spin 4 to D6, but the way I remember it is just the opposite of inert, which is D3, D8, and low spin D4 to 6. So an example to prove this is chromium 3 and iron 3. And these have a similar Gibbs free energy values, but they have different rates of substitution, and this is because chromium is D3, which is inert, so that will be slow substitution, and Fe3 is high spin D5, which is labile. Sorry, just sticking my paper. So that this means that the thermodynamic values are useless in terms of substitution. Another way to look at it is kinetic stability. So Mercury 2 has a much higher stability constant than iron 2 with substitution of water with cyanide. But this isn't in fact the case because they're both inert. Mercury 2 is D6 and iron is ionization number than the starting complex. The energy profile graph is the 2 camel humps. That was shit. What am I trying to say? Oh yeah, here's we've got our activation and energy, our intermediate, this is energy, this is reaction pathway, and then you could just put them terms in the separate points. The next is dissociative, which is similar to an SN1 two-step mechanism. This is where the old ligand X dissociates before the new ligand binds to the empty coordination site. So this can be drawn as L5X goes straight to K1, K minus 1, goes straight to just ML5 plus X, and then ML5 plus Y, K2, goes to ML5Y. And the energy profile is exactly the same as associative, the only difference being that the intermediate has a lower coordination number than the start material. That can be filled in the same way. Sweet. The last is interchange mechanism, or I, where the intermediate forms a transition state, which is, it's in between, so these two are two extremes and this is just in between. So it can be associative or dissociative on dissociative, D, not B. So it can be associative and dissociative. So associative is mostly making bonds and dissociative is mostly breaking bonds in the transition state. It's also a concerted process, which is one step. And the energy profile, the humps aren't as different because no intermediate is formed. Okay. So there are 3 thermodynamic factors we can use to predict the pathway. The first is using the E-ring equation, and this is to calculate entropy of activation and entropy of activation. So it's natural log over KT, where K is the formation constant, minus the activation of energy over RT, where R is the gas constant. I should probably be writing these in. Oops. New law. Which is 8.314. formation constant. Okay, and then we've got natural log R over Avogadro's number, which is 6.6.26 times 10 to the 23. More something, I can't remember. Enthalpy of activation, which is in joules per mole, and Planck's constant, which is 6.626 times by 10 to the minus, I think. And the entropy of activation is in joules per Kelvin per mole, just in case we get asked to do an equation. So what does the enthalpy of activation say about it? No, wait. So this equation is y equals mxc, where y is log over kt. Oh shit, k over t, sorry. Oh, right, yes, m is the enthalpy of activation over r, x is 1 over t, and this, which I can't be asked to draw, goes here. Right, so what does the entropy say about the mechanism? Flip that on the page. So a large negative value equals associative. And this is because there's a decrease in entropy. And similarly, so a dissociative is more positive because of an increase in entropy. We've got one problem, which is solvent reorganisation. Basically, solvent reorganisation gives a negative value of entropy of activation, which is not what you want. So the only way you can tell if it's associative is if it's really, really, really negative. Well, like, not really. I don't know. So the next one is pressure dependence of rate constants, which determines the volume of activation. So if the transition state has greater volume than the initial state, then it's negative. What? No, it's not. It's positive. So if the transition state has a greater than the initial state, then the volume change of activation is positive and associative. Yeah. Jesus Christ. No, it's not. It's dissociative. Oh, holy moly. Dissociative. And if it's negative, it's associative, which is the other way around than you would expect, but I'm just going to remember it like that. Right, okay, that's it. That's all the equations you need to know for substitution reactions.